Hello, my name is Daniel Segovia, and let's go on with the MOOC on wire antennas. The third part of this MOOC is devoted to line sources. It's important to call your attention that in the previous MOOC, we will conclude that the solution of the vector potential equation is the Fourier transform, the 3D Fourier transform of the corresponding charge, current, or charge density. If we simplify that problem, we are going on with what it is called a line source. And what is a line source? A line source can be defined as a continuous line source distribution whose electrical sources, currents, or charges are only function of one coordinate. In this way, the line source can be defined as a wire which is directed along the z-axis. We will take the z-axis because it will be easier when we try to find out the electric and magnetic field. So what we are really having is an electric current that is flowing through the line source. It can be simplified in the way I'm showing you at this very same moment. We have a wire, we have a line source that it is directly fed by a current along the z-axis. And we are trying to find which is the electric and magnetic field in a position far away from our corresponding source. Here we have in spherical coordinates the theta angle, and here we have the phi angle in spherical coordinates. And the other component is the r vector that is due in this direction from here. This problem from here can be quite similar to the corresponding discrete counterpart, and we could consider that this line source from here could be sampled in different positions apart from each other. So this problem from here is quite similar to this one from here. So the goal we are aiming at is to have typical current distributions, for instance, uniform, triangular, square, cosine, or cosine on a pedestal, in order to make the Fourier transform, in order to find which is the electric and magnetic field after finding which is the corresponding vector potential. So the radiation function of any line source is given by the Fourier transform of the current flowing through the line. It is very important to call your attention that the integral in the 3D domain that was presented in the previous MOOC can be replaced now with a 1D domain Fourier transform. So the first thing we are going to do now is to make a brief review of the Fourier transform. Any periodic signal can be expressed as a linear combination of complex exponential. Remember, for the easiest case, for the simplest case, the Euler notation. Secondly, what does it happen when I have aperiodic signals? Well, when I have an aperiodic signal, it can be considered as an infinite period periodic signal. But also, I can have that the complex exponential for the periodic case are harmonically related. Then the complex exponentials for an aperiodic case are infinitesimally close in frequency. So, in this case, the sum for the periodic case, what it is called the Fourier series, will be replaced with an integral in the in the aperiodic case, denoting the Fourier transform. So, finally, I have in this slide, which is the Fourier transform of a time domain signal, and here I have the inverse Fourier transform of this signal from here. If I skip to the antenna problems I'm dealing with at this very same moment, it's important for me to call your attention about two essential properties of the Fourier transform. The first one is the convolving property. Let us consider a linear time invariant system with its impulse response is given by ht, h over h of t. It is clear that the output to this linear system will be given by the convolving integral of the input signal xt with the answer of the linear time invariant system I am considering. And this is denoted in this part of the slide from here. If I apply the Fourier transform to this convolving integral, it is well known that the Fourier transform of the convolving integral is transformed into a product of the corresponding Fourier transform of the input signals x j omega of j omega and the corresponding answer of the linear time invariant system. If I summarize some typical pairs of Fourier transform, what I am trying to call your attention at this very same moment is to consider two or different typical excitation of antennas, current excitation of antennas. The first one could be a cosine fitting where the index of the corresponding potential of the cosine will be 0. This is the same as a corresponding uniform distribution, uniform current distribution that it will be denoted by this sketch from here. The Fourier transform of this uniform current excitation will be given the corresponding sinc function, the sine of u over u. If I have another typical current distribution, that is a triangular current distribution, I can also apply the Fourier transform, and I know that the Fourier transform is given by this expression from here, exactly the same sinc distribution from here, but at the square power. Okay? And finally, if I have a cosine on a pedestal, I know that the corresponding Fourier transform will be the sum of the corresponding Fourier transform of these excitations from here. So it's important for me to take into account that the corresponding electric and magnetic field is directly obtained from taking the Fourier transform of the corresponding current distributions. So if I call your attention about typical current distribution, the first one is a uniform current distribution. The second one will be a triangular current distribution. These two current distributions will give us, the uniform distribution will give us the maximum directivity of the antenna. That will be 1 in comparison with itself. And it will have that the beam width will be the smallest one and the side lobe level will be the highest one. If instead of having one uniform current distribution, I would have a triangular current distribution, it will have that the directivity will be diminished down to 0.75 times the corresponding of the uniform one, the beam width will be enlarged, and the side lobe level will be twice the previous one. This is very important because these conclusions from here are exactly the same for the continuous case than that for the discrete case. The continuous case is the corresponding one to the line source, and the discrete one will be the corresponding one to any array of any set of uniform sources. So, if the goal is to find out which is the radiated field by a line source, I can say that the radiated field by an infinitesimal line source will be given by this expression from here. But the most important part from this, at this very same moment, is to consider that if instead of having an infinitesimal set-directed line source, we will have a uniform line source that it is composed of multiple infinitesimal line sources, the corresponding electric and magnetic radiated field is given by an expression that it is quite similar to the previous one, since I have all these terms in common, but with the only difference that this is multiplied by another additional term. This is the most important conclusion from these slides from here, because I can say that the electric and magnetic radiated field, or the field pattern of any line source antenna, is given by the product according to the property of the Fourier transform that the convolving integral in the Fourier domain is transformed with the product between the two contributions. So the normalized field pattern I have will be given by the product of the elementary factor times the corresponding space factor. These conclusions will be general for any kind of line source, and we will make use of this in the following parts of this MOOC on wire antennas. Thank you very much, and I hope you have enjoyed on that.